Yes. So sorry for. We have submissions deadlines, lots of deadlines this week, and it's really tough. So can you hear me? Okay. So back again. I mean, next week it will be more organized. But I mean, for the last time, for this reviews, this database or data set, we have those reviews, for example, and these reviews, it consists of sequence of words, and each one, he will use his own language, his own words, to make it more systematic for machine learning. They just use the natural language processing techniques for getting the most frequent used words on all reviews. And for example, if we will represent each review as a vector of 10,000 values or 10,000 words, we will change, we will replace, in fact, each word here with a number. Imagine that the most frequent, I mean, as you can see here, for example, this one here. So this one has been replaced by one, maybe because this one, it's the most frequent, in fact, a word which is used in the list of 10,000 values. So this one will be replaced by one. Maybe this film, for example, will be replaced by 14, because maybe in this data set, film was number 14 in the list of the most frequent used words. For example, was replaced by 20, just was replaced by 16, brilliant was replaced by 43, casting was replaced by 53. Those numbers is the index of each word in the big vector. I mean, just imagine that we have a vector of or 10,000 most frequent used words in this one. So, for example, it will be like, for example, this will be number one in the list. Number two, I don't know which is number two. We have here number two, but I don't know which is number two here. Maybe this is S, maybe this is, maybe number two, for example, and so on. So we will code it. Each review will be changed into this one. So we will replace each word with a word from with the index of only the most frequent, by the way, only the most frequent. So we will ignore some words here. So if you have a word which is 10,000 plus, for example, we will just ignore it. So we will replace each word with the index of the word of the list of most frequent ones. And after that, now we converted this one into list of integers, this matrix now, right? And in fact, the length of this one, maybe it's less than 10,000. Of course, it could be less than, or it could be more than, but it's a list of integers of most frequent used. So we will ignore other values. And after that, we need to use one-hot encoding, because this one, it's just a list. We need to convert it into a matrix. And this matrix, in fact, it will be 10,000 maybe times 10,000. So it will be one-hot encoding. It will be like this one. So for example, the first one here, it's 1. So if the first line or the first row will be 10,000 values, 10,000 zeros, we will just change the first value to 1. So which means the first word in this review, it's this. The second one, it's 14, for example. So the second row, it will be all zeros, except at 14 here, it will be just 1, right? So now we are converting it into, and so on. And we will do it like this one. So at the end, we will replace, or we will represent each review by a matrix, which is 10,000 times 10,000 using one-hot encoding, for example. What if we have a word which has been used 2 times, for example? So maybe if it is used 2 times, maybe we can just replace, we can increase this number to 2, for example, and normalize it later on. Or we can just ignore it, for example. Maybe we can just pick only 1 time, or we can increase this one to 2, 3, 4, 5, according to the number of uses of number of repetitions in each of each word.
Can I ask a question about?
Yes.
Sometimes a word, a meaning of the word is inferred and should be inferred in a sentence. So if we just investigating these words independently, we take out these dependencies, correlations.
Yeah,
It's
yes,
like a
yes.
time series.
Yeah, they are destroying it here, in fact. Or maybe they are not destroying it because we are converting it into this one hot encoding. So maybe the order also, I don't know, maybe the order, I don't know if the order will have a meaning here because the order will be different, right? Because maybe you are starting with a word which is number 10,000 or 5,000, for example. So it will appear in the 5,000 location. So maybe we are not taking care of this context or the we maybe those
Just
independencies. Mhm. Because
um,
we are converting it now. It's so I mean we are converting each review into one hot encoding, and the size of this one vector will be 10,000. So it will be like the big vector like this one, and it's 10,000 values, right? Where it will be one when this word appears in the. So this one will be zeros, some ones, zeros, ones, zeros. It will be something like this one. So we are converting each review into one vector of 10,000 values using one hot encoding. It will be one if the word of this index appeared in the review. Otherwise, it will be just zeros.
yeah, it's
So
like
now, mhm,
okay,
if you,
it's because, in time
yeah,
series we also have some kind of when we investigate each samples
mhm.
independently, and their correlation and their dependencies would be ignored. So yeah,
because here we are not using, in fact, yeah, we are not dealing with it as a time series. In fact, we are just dealing it with a fixed input. It's like in shallow learning. Even in the model here, we will just build a normal feed-forward neural network, which consists of number of layers, for example. So we have here, this is the input layer. I use the sequential API from Keras. So we have how many layers here? We have this is one layer, two, three, four layers, four, five, six, maybe six layers, right? So we have here dense layer. So we have this is the first layer, drop out, second, drop out, third, this one four, and after that five. So we use the five feed forward, which consists of five layers. So what will be the input shape of the first layer? The input shape will be this one hot encoding, right? It will be 10,000 values. So the number of inputs of the input of the first layer, it will be 10,000 values. And of course, the number of outputs in the last layer, on the output layer, it will be two, because we have positive negative. So each sentiment, it's positive negative. So now we are not taking care of time series of the sequence. In fact, we are just dealing with it as a one vector. So now each review will be converted into a vector, and the size of this vector will be 10,000 values. So it will be 1 times 10,000, right? It will be like this one. Now we are not considering any independencies and stuff like this. So the input will be 10,000, the output will be 2, and in the middle you can just select how many layers here, how many units here. So 200, 512, 256, 64, right? And just to train your model, so we try to use metrics, its accuracy. We use the binary cross entropy, and we use Adam algorithm, for example. And we use the early stopping here. So we just make it, we use the early stopping so to avoid overfitting. And we use the dropout. We use those dropouts between layers to try to also avoid overfitting the problems. And just to train the model, we have the training data set. We have the validation, in fact. Um, So in fact, I used the first 20 values, 20,000 values for training, and the last it was 25,000. So the last 5,000 for validation. So this one, in fact, I used here 20,000 values for training and 5,000 values for validation. So the training data set itself, I divided it into two parts, one for training and one for validation. So the first 20,000, the training set is 25,000. We used the first 20,000 for training and the last 5,000 for validation. And I just trained the model for maybe 4 epoch. And we got an accuracy equal 87%. Yes. Do you have any question for this sentiment analysis? I mean, things are not organized today, I know, because I didn't have time to just polish the slides and try to make it more organized. Yes, do you have
What
any
is
question?
really this, sorry, what is this dropout doing?
Dropout? We didn't talk about dropout before.
Or maybe we did, but I missed it. But I don't know what does it do. I'm sorry if I missed it.
Yeah. In fact, the dropout, for example, I will draw here. Imagine that we have a hidden layer which has 4 units, 4 perceptrons or 4 units. And we have here some output layer, for example. And this one, maybe this one will be positive, this one will be negative, right? So it's a way of, we have here some inputs connected to this one. So in fact, dropout, we drop some perceptrons in the training phase. When we go forward, I mean, in the training, we go forward for calculating outputs, and after that we go backward for adjusting the weights. So when we go backward, we don't want to adjust all weights. So we drop some units, and when we drop a unit, we will not adjust weights connected to this one. So for example, if the dropout rate is 25%, so in this case, we have here in this hidden layer, we have 4 units. So in this case, we will drop out 1 each time by random when we go backward. So we will go forward. When we go forward, we use all output. We use all units because we need to calculate all those values connected to each unit. So when we go forward, we will just go forward as normal. We will calculate predicted value. We will subtract predictions from target values, calculate prediction error, and we will go backward using error back propagation to adjust weights. In dropout, in fact, if you don't have dropout, we will adjust all weights which are connected to those units, right? But in case of dropout, we will drop out some of those units, and we will not adjust the weights which are connected to those neurons. And in this case, it's like we try to train the model, but not all weights. We will not adjust all weights each epoch, for example. And in this way, we will try to reduce the capacity of the model to avoid overfitting. So it's like when you are studying, for example, you can just say, okay, I will cover one eye, right? You can just challenge someone. I will walk on a line. Maybe someone, he will just walk with 2 eyes, for example, open. And someone who will say, no, I will challenge you. I will hide 1 eye, for example, or maybe I will hide 2 eyes, for example. So I will just go like a blind, and I will walk on a line. So this is way of reducing the capacity of the model. So when we go forward, we will adjust all. We will just calculate predictions, calculate prediction error, go backward for adjusting the weights. When we go backward, we will not adjust all weights, but we will skip some weights. How can we decide this? For example, if we have here 4 units, 4 neurons, and if we have dropout rate is 25%, in this case, we will drop each time, we will drop 1 by random. So we have here 4 units. So maybe one time we will drop this one, the other time we will drop this one, the next 3rd time we will drop this one. So each time it will be in fact by random. And in this case, we will not adjust the weights which are connected to the dropped out neuron. So in this case, we are not adjusting all weights each time. We just train part of the model each time. We are not adjusting. We are not training the whole model each time. We drop out some weights. We drop those weights which are connected to those dropped out neurons. So this is dropout. And we have also early stopping.
One more question.
Mm-hmm. Yes.
In this case with the movie review, so for example, if someone uses a word, let's say fantastic or amazing or whatever, then it's classified as a positive review, right?
Yes, if it is, yes, it should be.
In a way, right? But what if previous word is not? So if someone writes, this movie is not fantastic. Like,
yes.
What happens in that case? Because that is definitely a negative review, or like not positive, right?
Yes, because in fact, yeah, there is no guarantee. In fact, there is no guarantee, but it's according to the data set. So maybe we have here some reviews which is not fantastic, not very good. But what do you think? Not fantastic, is it positive or negative? It's negative. Not fantastic movie. So in fact, this data set, it's based on the data set. I mean, in this data set, we have some people who have been reading those reviews and just annotate it. So you can just read this one and say, okay, this one looks positive, this one looks negative, this one looks positive, this one negative. So in fact, we have a data set which has been annotated by human. So this data set, in fact, it consists of 50,000 reviews. And some people, they have been reading those reviews, and you can just say, okay, this one positive, this one negative, this one positive, this one negative. And we will use this data for training a model. And after that, we will use the model to make, to classify new reviews, because we don't have people to, because it will cost money, of course. So we build a data set. So the data set will consist of some inputs, some outputs. The input will be the review. The output will be the sentiment analysis. It will be positive or negative. And then when you have a new example, we will test the model if it is really clever enough to say that, okay, not fantastic is negative, not very good is positive, because maybe not very good, it looks positive, right? So it's according to the data set. But this data set, I mean, this database review, in fact, we have input, which is the text, and the output will be just negative and positive, the target feature. So the input feature will be the text, the output will be this negative and the positive, and it has been annotated by human. People have been reading and deciding, okay, this one looks negative, this one looks positive, and we will use this data set for training a model, and after that we will test it with a data set. We have the example here, in fact. So you can just go to this link, and you can play with this example and try to modify it. So this is a link for this example in GitHub. And so in this example, we restrict it to 10,000, because this 10,000, maybe it's enough. You can just change it to 5,000. You can just say that, okay, I will code all those reviews using a vector of 5,000 values. So the most probable used, the most frequent used, 5,000 words. So, but here, in fact, I use the 10,000 words. Yes. This one, it's a binary classification problem. I mean, this internet movies database, it's a binary classification problem, because each review, in fact, is classified into negative and positive, only negative and positive. So it's a binary classification problem. There is also similar data set, which is Reuters data set, which is multi-class classification. In this multi-class classification, you can just say that, okay, I can classify movies into romantic, I can classify movies into different types of classes. So this Reuters data set, it's short news wires, and it has some topics, and it was published in 1986, and it used for text classification, and it consists of 46 topics, where some topics are more represented than others. So it's in fact unbalanced data set. I mean IMDb, it was balanced. This one, it's unbalanced. So each topic has at least 10 examples in the training set, and the data set consists of 8,982 training examples and 2,246 test examples. This is one example. So this is piece of news, in fact, right? And each piece of news will be converted into a topic, and we have 64 topics. 46 topics, right? So this is one example. And if you will have most frequent, so you can just you need to convert this one from this text form into this numerical form by replacing each word with the index of most frequent used words. So it's the same way as we did last time. So for example, here maybe said, it's most frequent. I mean, when we are talking about reporting news, usually they say said a lot. So maybe said, it's the most repeated one, most frequent used. Maybe as was number 2. I don't know, because we have here some repetition 2. So I don't know why we have 2 here. For example, 8, maybe 8 is result, or maybe a, correct? Maybe 43 is off, and so on. So we will convert this one from this form into this form, and after that, this one will be converted into a vector of one hot encoding. So for example, if you would decide to put it as a 10,000 a length of 10,000 word, for example, we will convert this one into a vector of 10,000 values. All those values will be zeros except when this word appear here, right? The list of topics, it will be also one hot encoding, and it consists of a vector of 46 values. All those values will be zeros except when it's this topic. You have also the same example here. So I used also represented each news wires into a vector of 10,000 values, right? And I build here a model which consists of how many layers? We have one hidden layer. So in fact, it consists of 3 layers, only 3 layers. So the first layer, the input to the first layer will be 10,000 values. So this one, the input to this one will be 10,000. The output will be 128. So the input to the second one will be 128. The output will be 32. So the last one, number of outputs will be 46, and the number of inputs will be 32 values. So it will be like this one. And this is the loss, and this is the accuracy for training, validation, and testing. Of course, I just trained it for 20 epoch, and you can see here that we have, this is the training and the validation. So we have here, what do you think? What happened here? Can you see? Do you have overfitting or something? From validation loss and accuracy, can you see that we have some overfitting? Do you have overfitting? So the training loss, it goes down. This is normal.
Question.
Yeah. So this one goes down all time. When we train the model, this one will goes down. And if we keep training the model, this one will continue going down, right? But the validation, it goes down, and after that, it started to go up, increasing. So we can just say that, okay, maybe we have here some kind of maybe overfitting, right? Here also for the accuracy, you can see that the accuracy for the training, it improves a lot, and this is normal. And if you keep training the model, this one will improve, keep improving until it's very close to 1. But how can we discover that we have maybe overfitting? That the accuracy here for validation, it improves, and some point maybe it looks like that it goes down, or so maybe we have a kind of overfitting point here, right? How can we avoid this one? We need to use early stopping. So we need to go back to the code here, and we need to use early stopping layer here. We need to use early stopping similar to this one here. I mean, in this example here, we use the early stopping. So maybe we need to use also early stopping in this code so we can avoid this. Do you have any question, Ali?
Yeah. Can you go to the figures?
Mm-hmm.
How do you have epochs in fraction? It's like 7.5 epochs?
No, it's not 7.5. It's just the grid, because when I'm plotting, I used a grid. So in the graph here, I used a grid. Maybe I don't have it here. You can have it in the code. But I bought something plot.grid. This one. So we don't have 7.5 in fact, but this 7.5, it is a grid from the graph. You can disable it. So you can just go to the code and try to disable it.
You have a point between the epochs. Like, it's not about the grid, it's about
this one? No. So this one it's 2. This one it's 1. This one 3. This one 4. This one here 5.
Oh yeah, I get it. Thanks.
Yeah, 6, 7, and so on. So okay. This is the number of epoch. But this is the grid. So you can go here to this code and try to. Yes. So yeah. So if I want to share the code with you, yes, this one. Yeah, can you see the code? So we use the keras, we import sequential, we import layers. From layers, we import the dense. For example, as I told you last time, if you want to plot some or to get access to some intermediate values, you need also to define model API from keras. So here we uploading the data, we define the 10,000 values. So we need to number of most frequent words. I will represent each review or each news, for example, as a vector of 10,000 values, 10,000 most frequent values. And this is my model. So the input to the first dense layer, it will be 10,000 values because this is the size of my vector. The second layer has 32 inputs. The last layer has 46 outputs. So 46 outputs because the number of topics is 46. So we have here 46. I mean, in Y train here, this one it's 46 values. 46 values. You will train your model. This is the total number of parameters. I didn't use here early stopping. Maybe you need to add early stopping. I trained the model for 20 epoch. Batch size is 128. So I mean, defining this batch size, it's a hyperparameter, but it's also connected with memory size, which you have. Validation split. I used this one, which means 80% of the training data will be used for training and 20% will be used for validation. So here, I mean, this one means validation split. So when you train your model, you will use 80% of X train, Y train for training the model, and the 20% will be used for validation. After that, you will get those figures here. So as you can see here, we have maybe some kind of, maybe we have a kind of, so the accuracy here, I don't know how much, there's just some examples. So we used here softmax, and those softmax, it will give you the probability that this news wire belongs to this topic, right? So it will just give you the probability. Maybe you need to have clear decisions that this one belongs to this one. So we can just use argmax here. We can get the maximum value using this one. So this one, in fact, it will give you the index of the topic which has the maximum probability. This one. So for example, I just used it for 5 values, for example. So for X test, so I tried to plot the first 5 values. So the first one was topic number 3, topic number 10, topic number 1, topic number 4, topic number 4, and so on.
What would happen if we were to use this early stopping? In a sense, how do we know when to stop?
No, I mean, it's like as we used it in the last example. So I mean, it's something when they feel that, I mean, when it sees that the loss for training, for example, started to increase, it will go back to the last epoch and it will just stop here and it will give you the weights from the last epoch or the last 2 epoch, for example. So it's just a command, in fact, which we use. So it will stop training automatically. It will not continue training because it's like a termination criteria. So for example, in this example, I said I want to train my model for 20. It will continue for 20 if you don't use early stopping. But if you use early stopping, it will stop at some point when the model starts to overfit. Because I don't want my model to overfit. I want my model to be able to generalize. So in this case, when we use early stopping, we will stop the training process at some point to avoid overfitting. So if we can go back to the slides. Yes. So this one, it's a multi-class classification problem, in fact. So we have 46 topics. And as you can see here, what is the difference? The difference is the output layer will have 46 outputs. I mean, last time, in the last example for binary classification for sentiment analysis of IMDB, we have only 2 because it was binary classification problem. But here it's multi-class classification problem. So in this case, we will have the output will be a vector of 46 values. Yes, we can talk about CNN, maybe briefly, for example. So the goal of CNN, in fact, it's to learn higher order feature in the data by convolution. So the convolutional layer is responsible for systematic application of one or more filters to an input. We have an input image, and we will apply those filters, and we will try to extract new features from those original images. So the architecture consists of 3 types of layers. We have some input layers, and this input layer, it's do nothing. In fact, it's just transfer inputs into the next layer. And feature extraction layers, and those feature extraction layers, it will be a sequence of convolutional layers. And the pooling layers, in fact, it will be a sequence of convolution and pooling layers. And at the end, we will have something called classification layers. Classification layers are fully connected layers. So the CNN model, in fact, it will consist of some input layer, a set of convolutional layers, right? And after that, fully connected layer. In fact, the fully connected layer, the input to the fully connected layer will be higher order or high level features. And the output will be the number of topics, for example, or number of classes, whatever. So maybe we have 1 fully connected layers or 2 fully connected layers at the end. Those fully connected layers, it's the layers which will make decision. The input to those layers will be the output from the convolutional layers, which is high-level extracted features. Convolutional, in fact, it's this structure. Usually it's convolution followed by pooling layer. Those pooling layers, in fact, the idea from those pooling layer is to reduce the dimension of the extracted features. Because at some point, I don't want those fully connected layers to be because this is a problem here, in fact, is this fully connected layer. The output from those the extracted feature maps will be delivered to the fully connected layers. The fully connected layers will use those feature maps for making decisions. So we use the pooling layers to try to reduce the dimension of the extracted feature maps. So we can have fully connected layers, which is really not very complex because this one can overfit. This one will not overfit, in fact, this one. So the convolutional layers, it will try to extract feature maps. So this one will be fine. This one will be okay all time. But the problem, if your model will overfit, it will overfit because of that part, fully connected part. And as we know from before, that to avoid overfitting, we need to reduce complexity of this one. We need to reduce number of weights in this one. How can we do this? By trying to reducing the size of the feature map. Because the size of the feature map will impact the size of this fully connected layers. Number of weights. You see here we have number of weights connected. I mean, we have here number of weights connected to each pixel value, right? So if the number of pixel values here is too much, number of weights here will be too big, right? And to adjust those weights, we need big data set. And if you don't have a big data set, this one will overfit. If your data set is small and the capacity of those fully connected layers is too high, that part will overfit your data set and your model will not be able to generalize. One way for solving this problem is to use this pooling layers. So those pooling layers, it's nothing. It's just a way for reducing the dimension of the extracted feature maps. So the fully connected layers, it will be responsible of classifications. Convolutional layers will be responsible of extracting some feature maps from my data. And the input layer, it will do nothing. It will just, receive inputs and deliver it to a first convolutional layer. So the building blocks of CNN models, we have those convolutional layers. we have those Boolean layers, we have those fully connected layers. Convolutional layers, it will not overfit, it's impossible. So the convolutional layers and the Boolean layers, those will just train to, it will learn to extract some feature maps from my raw data, and it will deliver it to the fully connected layers. So the one which might overfit, it will be the fully connected layer, right? What is convolutional? So convolutional consists of number of filters, and we apply those filters to the original image or to a feature map to generate a new feature map. Yeah, we will talk about it later on. But just in those convolutional layers, we have a filter, and we will apply this filter to an original image or a feature map to extract a feature map or a new feature map. So the filters, what are the filters? Filters are neurons of the layer. It's one layer. In fact, you can just imagine that it's one neuron, in fact. And this neuron has number of weights. So they have both weighted inputs, and they generated an output like a neuron. So the input size is a fixed square called a patch or receptive field of the filter. If the convolutional layer is an input layer, then the input patch will be pixel value. If they deeper in the network architecture, then the convolutional layer will take the input from a feature map from the previous layer. Yes, I want to explain this one. Yes, I will just try to draw it for you. So we have an image. And the convolution, we have a feature, we have a filter. We have this filter, for example, maybe it's 4 times 4. Imagine that we have a filter which is 4 times 4. We need to apply this one to the image and make some calculations. Imagine that we have here some numbers. Maybe this one, it's 1, 1, minus 1, minus 1. We have 4 numbers here. And this is the original image. So we will apply this one here. We will multiply those numbers with the pixel values underneath it. We call this area, it's the receptive field. So the receptive field, in fact, it's the filter size. So we will apply this one to the image. We will make some calculations, and we will get those numbers, and we will put it in the feature map. This one will be the feature map. So the first pixel value here would be the result from this convolution calculations. How many feature maps? How many filters we have? It's a hyperparameter which you need to decide. So how many filters? The size of the filter also, it's something which you need to decide by yourself. But you can just imagine that each filter is one neuron, and a number of weights connected to it. It's a number of the size of this filter map. So if this one 2 times 2, which means we have 4 weight values here. So you can just say that this one it's omega 1, omega 2, omega 3, omega 4. And the output from this one will be given here, will be stored here in the feature map. Right? So you can just imagine that when we define number of filters, so the first convolutional layer will consist of number of neurons. The number of neurons will be the number of filters. You need to decide how many filters. I mean, this is hyperparameter which we need to decide, but we will go back to it later on. Yes. So the feature map is the output of one filter applied to the previous layer. So in fact, each filter will generate one feature map. So when you decide here the number of filters, in fact, we decide number of feature maps which we need to extract by applying those filters to the input image. So for example, maybe this one, it's MNIST. So it's 28 times 28 pixel values, and it's 400 in digit. And we will apply, for example, 10 filters. So when we apply 10 filters to this image, we will generate 10 feature maps, 10 different feature maps. Right? So we will apply 10 filters of different numbers, and each filter will try to extract some features from the original image. So at the end, we will have 10 feature maps. So when you decide number of filters, you decide, in fact, how many feature maps you want to extract from this image. A given filter is drawn across the entire previous layer, moved 1 pixel at a time. So in fact, in convolution, we have a filter, and this filter we will apply it to the image, and each time it will move to the left by 1 pixel value or 2 pixel values. So just imagine it's only one step. So each step it will move 1 pixel by 1 pixel. We will make those calculations, and we will store the output value to the related pixel value in the feature map. Yes. So each position results in an activation of the neuron and the output to be collected in the feature map. I mean, we will have this. This is the original image, and we have a feature map. The feature map will consist of number of pixels, right? So each pixel, in fact, you can just say it's one activation, one calculation, because each pixel value here, it's generated by applying the filter to the image. So it's one calculation. You can just say it's one activation, because at the end, in fact, we can calculate how many activations we will do. So number of activations will be connected with the size of the input image. If it is big image, it will take more number of activations, which means more number of calculations. So we need computational resources. We need very high computational resources for deep learning, in fact. But we can calculate how many activations will be done. So the number of activations will be related to the number of the size of the image, width times length times width. If the receptive field is moved 1 pixel from activation to activation, then the field will overlap with the previous activation by field width -1. Because when we move the filter, in fact, we move it 1 pixel value each time. So you can just say that there will be some overlap between each activation, and the size of this overlap will be the field width -1, because we move it one by one. You can move it 2 steps each time. You can move it 2 pixels to reduce maybe the overlap and to reduce number of activations. So if your model is very, very slow in learning the training process, you can just increase the step size to 2. When we increase it to 2, in fact, we reduce number of calculations, we reduce number of activations. The distance that the filter is moved across the input from the previous layer, each activation, we call it stride. We call it stride size, in fact. So when we select stride size equal 1, it means the filter will move 1 step each time, 1 pixel each time. When you select stride equal 2, your filter will move 2 pixel values each time. So you can just imagine each application is one activation, is one calculation, right? If you need to reduce number of calculations, I need to increase the step size into 2, for example. So my model can train faster, right? We have something called the zero padding is used to is used to invent mock inputs with 0 values for the receptive field, not to read off the edge of the input feature. I will just tell you, for this padding, for example, you have this is the input image, right? And if I will apply my filter here, we can just, if it's 3 times 3, for example, I will apply my filter here, for example. So it will be like this one. So I will start applying my filter here. Padding means we need to add some 0 values on edges. So I will just add 1 row here and 1 column of 0 values around my original image. So when we apply those convolutions, the resulted, in fact, or the output feature map, it will be the same size as the input image. Because if you didn't use 0 padding, the size of the feature map will shrink each time. So it will shrink. And also, it's not only shrinking, but also it means we are not paying too much attention to the information which are located on the edges of the image. Because when we apply those filters, when we apply convolution, in fact, we have a kind of overlap. those overlap, it will the pixel values which are inside the image, it will get too much calculate. It will be used a lot, in fact, on those activations, which means we will try to focus on the information which are in the middle of the image compared to the information on the edges of the image. We will use it in the calculations, but we will use it for very few times compared to the pixel values which are located inside the image. So maybe if you are building a system for an autonomous car, so the machine learning model will try to focus on the information which is in the middle of the image, not close to the edges. But in fact, in reality, the information on edges are more important, because you can just imagine when you are driving, someone is crossing from the zebra cross, for example, but he is crossing from the edge of the image. If you didn't use zero padding, maybe the machine learning model will try to focus on the information in the middle of the image and not on the information which are close to the edges. So maybe you will hit someone because the machine learning model will not predict that we have someone who is trying to cross, in fact, because you can just see that he is trying to cross, so that we will see him in the edge of the image, not in the middle of the image. If he is in the middle, we will take care of him, we will stop. But because he is crossing, so he is coming in the image from the edge, right side, for example. He tried to cross the road, for example. So maybe the machine learning model, it will not take care a lot of people who are crossing or the information which are located at edges. So when we use zero padding, in fact, we will try to give it more attention. In fact, we will try to focus more on the information on the edges of the image. How convolution is done? So imagine that we have this image. This is the original image here. We will use zero padding, and we have a kernel or a filter of size 2 × 2. We will apply it step by step. So we will apply it to that part. I mean, the kernel has some values, which is 0, 1, 2, 3, for example. You will multiply those numbers by those 4 values. So it will be 0 × 0, 1 × 0, plus 2 × 0, plus 3 × 0. It's weighted sum, in fact, weighted sum. And the result will be given here. We will put the result here. So this is the input image. This is the input image with zero padding, and this is the feature map. We just call it feature map. So do you understand now from where we got this zero value? So by applying those 4 values to that part, we will get this zero value. It's weighted sum. So it's 0 × 0, plus 1 × 0, plus 2 × 0, plus 3 × 0. So we will get this zero value. Right? We will move it one step. If the stride equal 1, we will move it one step. So we will apply it to that part from the image. Multiply, so it will be 0 × 0, plus 1 × 0, plus 3 × 1, plus 2 × 0. So the result will be 3. So the pixel value here will be 3. We will move it another step. So it will be here. So this time it will be 0 × 0, plus 1 × 0, plus 2 × 3, which is 6, plus 1 × 2, which is 2. So total will be 8. So we'll have 8 here. We will move the filter by another one pixel to the right. So it will be 0 × 0, 1 × 0, 3 × 0, 2 × 2. It will be 4. After you are reaching the edge here, we will go back. We will go down, sorry, by one step, by 1 pixel, and we will repeat this one more time, scanning from the left to right. So we will start here. So it will be 0 × 0, 1 × 0, 2 × 0, 3 × 3. It will be 9. Move it one step, 1 pixel to the right-hand side. So it will be 0 × 0, 1 × 1, 3 × 4, 12. So it will be 13 plus 6. 13 plus 6, it will be 19, and so on. So this, imagine that you have this kernel size, and when we apply this kernel size to the input image with padding, we will get this output feature map. So you can just yes. So finally, we will get this feature map here. So zero padding, in fact, when we apply a convolutional layer, we lose some pixel around the perimeter of the input image. It can add up for successive convolutional layers. One solution is to add pixels of zero values around the boundary of our image. Because if we will apply those kernel layer by layer without zero padding, what will happen? This feature map will shrink all time. So this one will shrink with some value, and when we apply it, when we use it for another convolution layer, it will keep shrinking all time. So maybe we will lose some important information, especially those informations across the edges. So one way to keep this information is to use zero padding, because when we use zero padding, the size of the feature map will be the same size as the size of the original image. We move by a step. This step we call it stride. So the stride, it's by default, the filter slides 1 pixel at a time. Sometimes for computational efficiency or because we wish to downsample, we move our window more than 1 pixel at a time, skipping the intermediate locations. So sometimes if you want to simplify calculations, you can increase the stride size by 2b2, for example, or 2b3, for example, 4, 5, if you want to reduce number of calculations. So the stride, in fact, it's the step size at which the filter will move from left to right and from top to bottom. It's by default, it's one pixel by default, but you can change it to 2, for example, to 3, for example, if you want to skip some intermediate values and to speed up your calculation. Yes. So what is the Boolean layer? So now we know convolutional. We know convolution. What is convolution? This is convolution. But the building blocks of any CNN model consist of convolution layers and the Boolean layers. What is Boolean? Boolean, it's a way for reducing the size of the feature map. So the Boolean layer downsamples the previous layer feature map. So in fact, the input to the max Boolean, it does not have any weights, in fact. It's just a calculation, in fact. So you have the input, you have the output. And it's a way to shrink or to downsample the size of the input map. So imagine that this is the input, and we have 2 times the 2 max Boolean, for example, and we need to apply it to the input. So it will be like this one. We will apply it to, it's 2 times 2, which means it's 2 times 2. So we will apply it here first. When it's max Boolean, we will just pick the max value. So this we have here 4 values, 0, 1, 3, 4. So the max will be 4. And if stride equal 1, so it will move by 1 to the left, to the right. So we have those 4 values. So the maximum from those 4 values will be 5. We will go down by 1 step, and we will start again from left. So we will go to that part. What is the maximum value here? It will be maximum value. It will be 7. Move by 1 pixel value to the right. What is the maximum value? So the maximum value will be 8. So this is the output. So this is the output by applying max Boolean. So the Boolean layers, in fact, it's to follow a sequence of 1 or more convolutional layers. So you can just have a max Boolean after each convolutional layers, or a sequence of convolutional layers. So you can have a block of convolutional layers, for example, 2, 3, 4 convolutional layers, followed by a max Boolean layer. So they are intended to consolidate the features learned and expressed in the previous layer feature map. It's a way of consolidation of learned feature maps. They compress or generalize feature representations and generally reduces the overfitting of the training data by the model. So it's like data compression. So you have a feature map, and you need to compress this feature map or downsample it into a reduced feature map or consolidated feature map. So this one, in fact, it's feature map, and when we apply max Boolean, we will get this reduced feature map. This one was 3 times 3. When we apply it to 2 times 2 max Boolean, it will be 2 times 2. So you can just imagine how much reduction, right? You can just say it's a data compression. Data compression. And then when we use data compression, in fact, we try to just, simplify the model structure to avoid overfitting or to, So they have also receptive field, and the receptive field will be the size of the max pooling filter or max pooling size, and it's much smaller than the convolutional layer. The stride or number of inputs that the receptive field is moved for each activation is often equal to the size of the receptive field to avoid overlap. Pooling layers are often very simple, taking the average or maximum of the input value in order to create its own feature map. So this is max pooling. We can have also average pooling. In average pooling, we will sum those values and take average. So this one max pooling, when it's max pooling, this one will be 4. If it is average pooling, what will be the value here? It will be 0 plus 1 plus 3 plus 4 divided by 4. So it will be 2. So this one, it's average pooling. So the first pixel value here, it will be 2. It will be 1 plus 3 plus 4 divided by 4. The second one, it will be 1 plus 2 plus 4 plus 5. So it will be 6. 6 plus 6, it's a 12. 12 divided by 4, it will be 3. Right? And so on. So we have max pooling, we have an average pooling. You can just create your own pooling approach. But you can just say that it's data compression, because now the input feature map was 3 times 3, the output is 2 times 2, so we are compressing or consolidate those feature maps. So if the building blocks are convolutional layers, pooling layers, fully connected layers, we have been talking about convolution, we have been talking about pooling layers. What is else is the fully connected layers. Those fully connected layers, they are responsible of decision making, in fact. So we will have here, this is the input volume, input image. So imagine that it's a 32 times 32 picture, for example, or image. We will have some convolutional layers. We will have some convolutional layers and the max pooling, followed by some max pooling. So at the end here, we will have some feature maps. So those feature maps, it will be converted into a vector, right? So we will flatten. At the end here, before any fully connected layer, we have something called the flatten layer. Flatten layer, it's nothing. In fact, it's just converting any feature map into a vector values. So we'll have this flatten layer. So after any convolutional block, we need to have this flatten layer. This flatten layer, it will convert the feature map from its own dimension into one vector. So it will be converted into this flatten layer. And after that, we will have the first fully connected layer, be the second fully connected layer, and so on. So imagine that this one, it's a fully connected layer number 1, this fully connected layer number 2, for example. So after flatten, we will have here a number of units, maybe it's 20, right? And I don't know the size here, the output volume here will be 588, right? So after flatten here, we will have 588 values, and the fully connected layer has 20 units. So those values will be connected to all those units, right? So how many weights we will get here? Can you calculate it? How many weights? So after flatten, we will have the first fully connected layer, and after that, the second fully connected layer. We need to decide number of units in the first fully connected layer. We need to decide the number of units in the second, or the output layer, for example, this output layer. Of course, the number here will be the number of classes. So don't need to specify this one, in fact, because the number of units here will be the number of classes. But can you calculate number of weights here for this one? This one has 20 neurons, and the output volume here has 588. So if we need to calculate number of weights here, it will be 588 times 20 plus 20. Is it correct? So the number of weights here will be number of output or output volume here. It will be 588 times 20 plus 20. Yes, sorry. So it will be this number. What will be the number of weights here in the output layer from the FC1 to FC2? What will be the number of weights? We have here 5 classes. So how many number of weights here?
20 multiplied by 5 plus 5.
Plus 5. So this is, and this is a problem, in fact, in deep learning. Those number of weights, this is a problem because that part can overfit easily. Right? If you want to reduce this number of weights here, we need to reduce this output volume. And to reduce the output volume, we need to play with Boolean here, Boolean layers. We need to add more Boolean layers, right? Because at the end, the output volume here will be equal to the size of the feature maps generated from here. If you want to reduce the size of those feature maps, you just need to use Boolean layers, more Boolean layers. So for example, maybe this one is 32 times 32 image or 28 times 28 like in MNIST, for example. You can use convolutional layer followed by max pooling layer, followed by convolutional layer, followed by another max pooling layer. So we use the two max pooling layers 2 times. So in this case, we can try to reduce the size of the generated feature maps. And when we reduce the size of the generated feature maps, we will reduce the output volume. And when we reduce the output volume, we will reduce the size of FEC1, for example. Not FEC1, in fact, we will reduce the number of trainable parameters here. We will reduce it. So instead of being 1 million, we can reduce it to 500,000, for example. So in this case, we will reduce the model capacity and we will minimize the chances of overfitting. So fully connected layers are the normal, flat, feed-forward neural network. It's just normal, feed-forward neural network. These layers may have nonlinear activation function or softmax activation functions in order to output probabilities of class predictions. So I mean, this is a fully connected layer. It's normal. You need to decide which activation function you want to use. Fully connected layers are used at the end of the network after feature extraction, and consolidation has been performed by convolutional and Boolean layers. So we will have here raw image, raw data, and after some layers of convolution and Boolean, we will get some feature maps. Those feature maps will be flattened here, and when we flatten it, we will decide how many fully connected layers we need here at the end. Those fully connected layers will be just normal feed-forward neural network, which will be in charge of decision making. It will decide if this image is class 1, class 2, class 3, 4, 5, and so on. Fully connected layers are used at the end of the network after feature extraction and consolidation by convolution and Boolean layers. They are used to create final nonlinear combinations of features for making predictions by the network. So this is the one which will make decisions. In Keras, in fact, implementation in Keras is very, very simple. So Keras provide an implementation of convolutional layers. We call it Conv2D. It requires the expected shape of the input image. We just need to decide the input shape in terms of maybe height, width, and depth. So the filter contains the weights that must be learned during the training of the layer. The filter weights represent the structure of the feature that the filter will detect, and the strength of the activation indicates the degree to which the feature was detected. The layer requires that both number of filters be specified and that the shape of the filter be specified. You need to specify how many features you want to use and what is the filter size. Someone will select 2 times 2, maybe someone else will select 3 times 3, 5 times 5, and so on. The number must be odd number because we are just applying it. It should be. Oh, it could be also. I don't know if it could be an even number. I have no idea. Yes. So the building blocks in Keras, in fact, it consists of those 4 steps. First, we need to create the model. and after that we need to configure the model, training, and after that evaluation and prediction. So first, from Keras models, we need to maybe import sequential and the model API. You can build your model as a sequential, you can build your model as a model, but in fact in sequential it's easy to deal with. And the model, it's nice for plotting some intermediate values. So after building your model and training your model, you can define a sub-model from the trained model and try to plot or get access to some intermediate values. From layers, we need to import dense layer. Dense layer, it's fully connected layer. It's like feed-forward. We call it dense layer. In Keras, we call it dense layer. So this dense layer, it's just normal feed-forward neural network layer, for example. For convolution, we can use Conv2D, for example. This is convolutional layer. And for max pooling, you can just use max pooling 2D, for example. So if you want to build your first deep learning model, you can just go for Keras, start with sequential API, and from layers, you need to import dense convolutional Conv2D and the max pool 2D, for example. So this is how we build the model. We just import this sequential API model. We call just model equals sequential. And in this sequential, we will just add some layers. So if I need to build feed-forward neural network, which consists of 2 layers, for example, so I will just add dense, number of units will be 64. This number of units will be the number of neurons, in fact. This is the number of neurons. What is the activation? You need to define if it is ReLU, for example. And the input dimension will be 100. So number of inputs will be 100 values. Or the vector size will be 100. So this one, how many weights here from this layer? Can you calculate it? How many weights? For this first dense layer, how many weights? How many weights we will get from this one? This first layer. This model now, it's 2 layers. This is 1 layer. And the second layer, it will be this one. In the second layer, we use the softmax. So we will have here number of classes, maybe class 1, 2, 3. So this is number of classes. So we have 2 dense layer. Here, how many inputs here now? How many inputs? 100 values. So we will have here 100 values. Number of units in the first dense layer will be 64. A number of units in the output layer, it will be 10 classes, for example. So how many weights here? How many weights? How many weights here? So it will be 100 times 64 plus 64. So this layer, in fact, it will generate 100 times 64 plus 64 bias. The output layer, it will generate 64 times 10 plus 10. So this one, it will generate 64 times 10 plus 10. So if you want to calculate number of parameters, you can just calculate number of parameters in this way. So in Keras, it's very, very simple. After building your model, you need to configure your model. You need to select loss function. You need to select the optimizer. You need to select also the metric. Is it accuracy? Is it prediction error? Whatever. So you need to configure your model. And after that, you will train your model. When we train your model, we train it using X-train, Y-train. You need to specify number of epochs. You need also to specify the batch size. Using this batch size, you can find how many batches. Divide the size of the training data by batch size to get number of batches. For validation, you can also specify validation here. Because when you fit your model, if you will use early stopping, for example, so it's recommended to use a validation set for checking validation error and validation accuracy, as we did last time here. You see here, we used it here in this example. We used it here. So in early stopping, we used the validation, we used compile. No, it's not here. Okay, so this one, do you see? Validation data. So you can specify the validation set correct? You can specify it, for example, and yes. So this is model fit. So you need this validation set specifically when you will use early stopping, or just if you want to be sure that your model is not overfitting. Because after training your model, you can plot history, you can plot training and validation error and accuracy, for example, and you can see if your model is overfitting or not overfitting. But if you want to stop it while the model is trained, you need to use early stopping. Yes. So after training your model, you will just evaluate your model. So when we evaluate our model, we evaluate it with a test set, X test, Y test. So we will get this loss and the metrics, loss, accuracy, metrics stuff. And after that, in deployment part, we will use the model for prediction. So when I deploy my model, for example, for face recognition, maybe it's implemented in a robot, for example. So we will get this image from outside from the camera. We will apply it to the model to predict what is the class. Yes. If you want to understand what is convolution, in fact, what is the filter, what is the kernel, it will work like this one. What is the meaning of convolution? We have an input image, and we need to extract some feature from the image. So we apply a filter or a kernel to the image and try to extract some other information. Maybe it could be low-level features or high-level features, for example. Of course, when we apply those vertical edges and horizontal edges, we try to get some low-level features from the image, from the original image. This is an example. There is something in image image processing. We call it edge detection, for example, is used for image segmentation. We use this one if you want to segment an image. We need to use those edge detection. And those edge detection, it could be vertical or horizontal, for example. And it creates boundaries of an object to detect the object location. So, for example, you have something in the image, and I want to find the location of an object in an image. So first, I need to segment the image and try to find the location of the object in the image, or just say that, okay, the object is in the image or not. How can we do this? Using some convolution, in fact, filters. And there is a set of filters which are defined in literature. For example, this one, it's used for vertical edge detection. So we can just try to detect those vertical lines from those images. And the horizontal, we can try to find those. For example, this one, we will get this one. We will get this line, right? So we can detect those vertical and horizontal edges in the image. This is an example of vertical edge detection. It's 3 times 3 vertical or kernel, this one. And we need to apply it to this image. Imagine that this image is an image which has this line. I mean, when you plot this image, in fact, when you display this image, this is pixel values equal 0, which is black, and the pixel values equal 10, which is white. So in fact, in the middle here, we have line. So the difference between this one, it's white, this one, it's black. And a line, in fact, it's a line between black and white, correct? So we have this image. This one, it's black, this one, it's white, and I want to detect this, the boundary between the two areas, in fact. Because the boundary between the two areas, it's an edge, correct? So I want to detect this one. I want to see that. I want to see this one. So how can we get this from the image? By applying vertical edge detection. And this is the vertical edge detection. It could be 3 times 3, 5 times 5, whatever. So we will apply this one. Those numbers, people who are domain experts in image processing, they decided that those numbers are very good for detecting edges. And we will see how, in fact. So just imagine that we have this one. This is the original image. And I will apply this vertical edge detection to this image to get this one, in fact. Right? So what does this one mean, in fact? It means that it's black everywhere except at the edge. So in this case, we can detect edge, because this one, it's called the edge detection. I want to detect this edge here. And when I want to detect it, I will convert the pixel which is close to the edge into white, and the rest will be zeros. Right? So how can we do this? By applying this filter to the image. So I will apply this one here to that part. Imagine I'm applying this one to here now. And I will calculate this number, and I will put this number in this pixel. So just multiply y times 10 plus 1 times 10 plus 1 times 10 plus 0 times 10 plus 0 times 10 plus 0 times 10 minus 1 times 10 minus 1 times 10 minus 1 times 10. So the result will be 0, in fact. So the pixel value here, it will be 0. And the 0 is black. Correct? So this pixel value will be 0. Because in fact, in that part, I didn't detect any edge. This is black, right? So this black area will be converted into just a black, sorry, this white area, it will be converted into a black pixel. Is it okay? So we are not detecting any edges. I didn't see any edges, in fact. Now we will move the kernel to the right-hand side by 1 pixel. So we will apply it to that area. Do you see here what happened here? Now, in fact, I have an edge, which is the boundary between white and black. That part, I should be able to detect it, correct? Apply the filter to that part. So it will be 1 times 10 plus 1 times 10 plus 1 times 10 plus 0 times 10 plus 0 times 10 plus 0 times 10 minus 1 times 0 minus 1 times 0 minus 1 times 0. So in fact, it will be 30. So the result here will be 30. And the 30 is white, correct? 30 is white. So we will have a white pixel here. We will have white pixel here. Correct? And so now we are moving from black into white, which means we detected an edge. Okay, I will move again with 1 pixel. So I will move in that side by another pixel. So I will apply my filter to this area. And I will apply those numbers again. So it will be again 30. 1 times 10 plus zeros. So it will be 30. So we have generated another white pixel. Because I still have an edge here, in fact. So this filter is very clever, in fact. Once we have an edge, we will generate white. We will generate a number, positive number, and this positive number will be represented as a white pixel. Because when it's 0, it's black. When it's 1 or big number, positive number, it will be white. So now the filter will be able to detect, still able to detect the edge here, and it will convert it into white pixel. We will move again 1 step. So here it will be only zeros, which means black. Is there any edge here? Do you see any edge in that area? This receptive field? Do you have any edges here in that section? That part? Do you have any edge? No, we don't have. Because all this area, in fact, this receptive area, all this receptive area, in fact, it's black. So we will generate just a black pixel here, 0. And we will go down by 1 step. So we will start again from here, but we will go down 1 step here. We will go back here, and we will apply it here to that part. And we will repeat this process. So at the end, my filter will be able to convert the edge as a white area in the image. Right? And if you go back here to this image, in fact, do you see those white areas? So my filter was able to, in fact, detect those edges, and they can convert those vertical edges into white lines. So which means we can detect those white lines. Right? So for example, I mean, imagine that you have a drawing of a building. For example, you have a house and an image, and in this house we have a door, for example, and a window. It will be like this one. When we apply this filter to the house, we will be able to detect only vertical edges. So at the end, I will have a drawing which is black everywhere except those vertical lines. This one, but sorry, this one will be white. This one will be white. This one will be white. Only those white lines, those vertical lines, we will be able to detect those vertical lines. So we have one filter which will be able to detect those vertical edges. We need to have another filter which will be able to detect the horizontal edges. Maybe we need to have another filter which able to detect some lines with some angles and so on. And at the end, we will mix those together to generate something which has a meaning, in fact, right? Yes. So now we apply the vertical step by step each time, and each time we will generate those numbers. Yes, and at the end we will be able to get. At the end we will be able to get this, generate this graph. So this graph, it will be black everywhere except at the edge. It will be white. So now we are able to detect those vertical edges. And imagine this is only one vertical, one kernel or one filter. But in deep learning, in fact, we can ask the machine to generate as many as of those kernels, and it will be generated automatically. I mean, here we generated those. We are able to detect those vertical edges based on the filter. And the one who made this filter, in fact, he is a domain expert. He is a mathematician, and he just find a way for solving this problem, and he come up with those numbers. And if we use a filter with those numbers, we can detect those vertical edges. But in fact, in the machine learning, we will initialize those numbers with random values, and the machine itself will try to come up with numbers which are clever enough to detect something useful for the problem which we are solving. We will not ask the machine, we will not give those numbers to the machine. The machine will initialize those numbers by random, and the learning algorithm will try to adjust those numbers in a way to extract something that has a meaning for the problem which we are solving. Because in machine learning, in fact, this kernel will be a kernel of weight values. It will be omega 1, omega 2, omega 3, omega 4, omega 5, omega 6, and so on. It will be like this one. So it will be weight values. Because each filter, in fact, will be a neuron. In fact, each filter will be a perceptron connected to the receptive field by number of weights. So it will be like omega 1, omega 2, omega 3, and so on until omega 9. So in fact, each filter in deep learning or in the convolutional layer, each filter will be associated with a neuron, and each neuron will be connected to a number of weights. Number of weights will be the size of this filter. And in the training process, we will initialize those weights with random values, and the optimization algorithm will try to adjust those weights until we have something that has a meaning, in fact. So we will have an example, and from this example, we will print those values. We will try to get those numbers to understand how the filter look like. But just imagine if you are working manually with your data set, what is your capacity? I mean, how many filters you will apply? 2, 3, 4, 5, 10 maximum? And you will do it from your point of view, in fact. So maybe someone who will say, okay, I want to detect an object in the image. So I feel that, okay, vertical edge detection, horizontal edge detection will be enough, right? So maybe from your point of view, those two filters will be enough. It's enough for you, in fact. It's not enough for the machine. But when we use convolutional layers in the machine itself, we will give the machine the freedom to select, to decide how the machine will build those filters. You will select how many filters, but the machine itself, it will decide how the weights will look like, right? So those are other examples. This is the vertical. This is the horizontal. This is a horizontal change, vertical change. So do you see? When we change numbers, we will be able to detect something different. It will be more complex. It will be more stronger for us to detect other things, in fact. So just imagine that this one, it's 3 times 3. When we change those numbers, from this one to this one, we are able to, instead of detecting vertical edges, we are able to detect horizontal edges. And then when we change numbers from this one into this one, we will be able to detect horizontal change. We will be able to detect vertical change. But how many filters in live? How many filters? Right? So this one we call it Sobel filter. This one it's a vertical edges, horizontal edges. So if you can just open any image processing book, you will see how many filters we can use. There are some filters in literature which we can use for manual operation of for manually extracting some features from images. Yes. So do you have any question about those edges, about filters, the meaning of those filters? It's just I want to okay, maybe later on. Okay. Yes. Okay. So what about padding? So what about padding? Padding, it's I mean convolving an image of 6 times 6 dimension with 3 times 3 filter. It will result in 4 times 4 output. So if we didn't use padding, in fact, the size of the extracted feature maps, it will shrink all the time. Why it will shrink? Because of this. Imagine that this one is 6 times 6. So if it is 6 times 6, maybe it's like this one. Maybe it would be hard to plot it. Just imagine that this one, it's like this size, for example, and I'm using this one, it's 4 times 4, and I'm using a filter size of 2 times 2. No, we cannot use 2 times 2. It should be a odd number. Sorry, it's not. Okay, 1, 2, 3, 4. This one, it's 4 times 4, and I will use filter of size 3 times 3. So I will use it here. I will make this one will be the receptive field, and I will make calculations and I will put it here. So the output here will be like here. And I will move it one step and I will make calculations here. So it will be, so the output, in fact, it will be like this one. It will be 2 times 2. Do you see? The size will be reduced by 75% if you didn't use padding. So this one, it's input image of 4 times 4. And then when we apply it, when we apply a filter of size 3 times 3 to this one, the output size will be 2 times 2, right? So the size will shrink. If you don't want the size to shrink, you need to use padding. So we need to add column and rows of zeros around the input image, so that the output size will stay the same. So we can generalize it, and it says that if the input is n times n, and the filter size is f times f, then the output size will be n minus f plus 1 times n minus f plus 1. Right? So we can test this example here. N equal 4, and filter size equal 3. So what will be the output size? It will be n minus f plus 1. N minus f plus 1, so it will be 2. So n minus f plus 1, it's equal 4 minus 3 plus 1 equal 2. So which is the size of this one. So if we didn't use padding, the size of the output feature map will shrink. If the input image size is n times n, the filter size is f times f. So the output image will be n minus f plus 1 times n minus f plus 1. So it will shrink. So there are primary 2 disadvantages here. Every time we apply convolutional operations, the size of the image shrinks. Each time, if you didn't use padding, and if you will use number of convolutional layers, what will happen in this case? So each time the size will reduce by the size of the output image will shrink. Pixels present in the corner of the image are used only few numbers of times, because imagine that this one here, we have this one will be used only one time, in fact, because next time we will move one step here, one step back here. So this one will be used only one time. Maybe this one will be used maybe 2 times. Maybe this one will be used 3 times, and so on. So the pixel values which are located at the corner of the image will be used only very few times during convolution as compared to the central pixels, leading to information loss. So the pixels which are located in the middle, it will be used a lot. But the pixels which are located at the corners and at edges will be used very few times. And this will lead into some information loss. So in this case, in fact, the model will pay attention to the pixels which are located in the center, not to those pixels which are located in the corners. And as I told you, sometimes it's very, very important to pay attention to the information which are coming from the corners and edges. Just imagine that you are building a system for an autonomous car, for example, maybe quadcopter, for example, right? So in this case, the information which are coming from edges or from corners, it will be scanned only one time. So it will not be given, in fact, too much attention by the model compared to the information which are in the center of the image. So in this case, we need to use padding, and when we add padding, we will add to overcome these issues, we can pad the image with an additional border. We add 1 pixel all around the edges. We can add just 1 pixel, 10 pixel, all around the edges, and this means that the input will be 8 times 8. So if the input image was 6 times 6, when we add padding, it will be 8 times 8, correct? Because we added 2 top, bottom, and the 2 left and right, so it will be 8 times 8. This means that the input will be 8 times 8 matrix instead of 6 times 6. Applying convolution of 3 times 3 on it will result in 6 times 6. So it will be, we will see what is n minus f plus 1. N minus f plus 1 in this case. N becomes 8, f is 3 plus 1, so it will be 5 plus 1, it will be 6. So we will go back to the original size of the image if we used 0 padding. So if you want to keep all information, if you don't want to lose any information from edges and from corners, you need to add 0 padding. So there are 2 common choices for padding. It's just adding it or removing it. So one choice is valid. Valid means no padding, in fact. It's strange. So when you select padding equal valid, it means we are not use 0 padding. So if we are using valid padding, the output will be n minus f plus 1. So the size will shrink. And the other one called same. When it's the same, in fact, we apply padding so that the output size is the same as the input size. The output size will be the same as the input size, which will be n plus 2b minus f, because we added this padding. So it will be we adding two pixel values. We add 2 pixel values to the size. So the final size of the output image will be n plus 2b minus f plus 1, which will equal to n. In this way, we don't lose a lot of information and the image does not shrink either. So in this case, we don't lose information from images, from corners, and from edges, and the output size will be the same as the input size. We will finish 12. I will finish at 12. Yeah. Is it okay to take maybe? Okay. Yeah, 5 minutes break. Is it fine?